Hello, everybody. I still see a bunch of people logging in. This is week 11, RT100, and hopefully everybody enjoyed their spring break. I see lots of people logging their names into the chat, so I see more people here than there are in the chat. So go ahead and get your name in there so that we have that record and know that you're hearing us. So both Professor Friedman and I are here. And I wasn't here with you guys last time, but I hear things went really well. And Professor Friedman and I are going to split the lecture today. We are doing chapter 7. We're going to do chapter 7 for 2 weeks. So we're going to get through about half of the chapter today. Before we start, we're going to go over some information about what there is to do for the next 2 weeks. So I'm going to go ahead and screen share with you in a second here. Okay, so hopefully you guys are seeing my screen of the modules for your Canvas shell. So we are looking at week 11, chapter 7. This is the chapter about radiographic imaging. So the first thing I want to tell you guys is that we're coming up on 3 very difficult chapters. And what I want you to understand about them is that these 3 chapters represent almost a year of education in the radiography program, okay? So we try to go over it as simply as possible, with just really basic facts without getting too in depth into everything, although it's going to feel like it's very in depth. Okay. So I want whatever, if you haven't been putting good effort in up to this point, this is when I need you to really lock in and start paying attention. These are the 3 chapters. They're going to tell you how difficult the program is in content. Okay. So what I want you to pay attention to on your to-dos is you're going to be having access to the PowerPoints within the lecture videos and PowerPoints, okay? You are going to have a quiz, obviously, but I want you to note that it's not due for 2 weeks, okay? So not due for 2 weeks because we're going to be doing this for 2 weeks. Discussion 9 is exploring topics in radiography education. And what that is you're going to take the book that we're using and you're going to look for a different chapter after chapter 10. So chapter 10 going forward, I want you to choose one of those chapters. And when you do that, you're going to answer the questions in this assignment about that chapter. Okay. So you're going to be making a discussion post, and what you're doing is you're educating everybody else in the class on the chapter that you chose. Okay. So exploring topics in radiography. That one is due in 2 weeks, okay? What's due next week is the exposure formulas worksheet. So part of the lecture today is going to be the math involved in this chapter. There are 4 types of math problems, okay? So part of the reason that you take this class is not only to find out whether this is something you want to do, but it's to tell yourself what you need to do before starting the program. And one of those things might be going back and relearning algebra. Very basic algebraic functions are going to help you in the program. And so even if you don't do very well in this chapter because of the math, I want you to know that this is for you to figure out what you need to do to prepare. Okay. So but there are some timeline things I want you to understand about this particular assignment. So first, you're going to download the exposure formula worksheet. It has tips on it for each type of math problem, okay? And you're going to print that out and fill it out, or use it as a PDF if you can, okay? You have to give us your answer and show your work in the worksheet. We're not going to give you the points if you don't show your work, okay? But there are 2 deadlines. The first one is a week from today, but at 5 p.m., not at midnight like you're used to, at 5 p.m., because we're going to review this when we get back here next week. Okay, so you're going to turn this in, do your best, right? We will grade it. There is a rubric with the answers in it, which you cannot see right now. You will see it after the due date. Okay, so if you turn it in and you get half of it wrong, then you get half the points. But if you do turn it in then you have the opportunity to submit it again with the correct answers that you will find in the rubric. And I'm assuming all of you know how to see the rubrics now because you know how to go to your grades, right? So when you go to your grades and you click on the little rubric icon, you'll see the answers. It's not there right now. It's going to be there next week after 5 p.m. If you do turn your stuff in by that time, you will be allowed to turn it in again. And you will have to obviously put the correct answer there, but also show your work again, proving that you knew how to get to the correct answer. Okay. The other thing that's going to be on there, which isn't there right now, is I'm going to assign you a we video like we did back in like week 2 or 3 when we looked at that, when you guys watched Joe's broken arm. Okay. And those we videos are going to be the videos that are in chapter 7. And honestly, neither Professor Freeman and I have managed to get our internets to work where the computers are sitting in our houses right now. And rather than making you watch choppy YouTube videos with us tonight, when we get there, I will you'll see where they typically fit in, and then you'll get a we video assignment. I'll have it up tonight for you to watch by next week. Okay. Let me just stop sharing for a second. Okay, so before I continue on to the actual lecture, I want to see if anybody has any questions. I hope some of you already looked at chapter 7. Is there anything that you have to ask us since we're both here going forward in the class that you want to pipe up and ask right now? Okay, so I'm going to remind you all to have your chats open so that you can ask questions in there. I'm going to lecture for the first part, and then Professor Friedman's going to do the second half when we get to the math, and we will try to watch the questions in the chat. You are free to interrupt us at any point. This is a difficult topic, okay? This topic's difficult whether you're in the program or in RT100 or you're a technologist. These are difficult topics. So I want to make sure that you know we are doing this for 2 weeks so that you can ask questions. Okay. So so keep your chat open or go ahead and interrupt us and we'll just stop and we'll talk about it. Okay. So everybody should be seeing radiographic imaging, Adler, Carlton, and Stewart, chapter 7. Okay. So what are our objectives for chapter 7? So let's just read through them. Okay. So we're going to discuss primary, scatter, and remnant radiation, discuss or describe the fundamentals of image production, discuss radiographic quality in terms of density, contrast, recorded detail, and distortion, list the major factors that influence radiographic quality, differentiate sharpness of detail from visibility of detail, perform basic calculations using milliampere seconds, inverse square law, exposure maintenance, and the 15% rule formulas. And that's what we're going to talk about tonight, okay? So this is the X-ray tube. We looked at this. I want you to pull your brains back all the way to the first time that we got together in person, and we looked at chapter 1, and we did a really basic introduction into the X-ray tube, okay? So here is what the X-ray tube looks like on the inside. And we're going to go over this for the next few slides to give you an idea of just the really basic components inside of that tube that produce the X-ray beam. Okay. So going through this, I'm going to kind of point, hopefully you see that motion there. So there are 2 sides to the X-ray tube. There is a positive side and there is a negative side. And the reason that we need that to be that way is so that when we apply the voltage, the electrons will move across the tube. Okay, that is the nature of physics that helps that to be the case. You have to have a positive side and a negative side. Okay, so on one side is going to be a filament. just like an old light bulb. Okay, so we're starting with the basics of a filament. And what does a filament do when you apply amperage to it? It heats up. Okay, and what it's going to do is it's going to heat up so much that it's going to boil off electrons from the filament coil. Okay, and it's going to create a cloud of electrons that are just waiting for something to happen until you apply voltage, and that's going to move the electrons across from the filament over to the target or the anode. Okay, and that is what is going to produce the X-ray, because you're going to have rapid acceleration of electrons hitting a target where it decelerates rapidly, and that creates our X-ray beam. Okay, so in here, we've got the cathode, that's the filament there. This is the cathode. Over here, we have the target, and the reason it looks so large is because it's on a turning mechanism and it'll turn, okay? This one looks like a stationary one, but they can turn, all right? And then you're gonna have a glass envelope. This is important because this all has to happen in a vacuum. Without the vacuum, no electron cloud, okay? It has to happen in a vacuum. So there's going to be a glass Pyrex envelope. And then you're going to have the anode, and the beam is going to come out a little window. It doesn't, not an actual opening in the glass envelope. It's just a thinner layer that lets the beam through, okay? So here's one of the first video that I'm going to have you in a Wii video for you to watch, okay? But we'll go past it. So on the right-hand side, you see the actual image of what the X-ray tube looks like inside of the actual like outer metal casing, okay? So you can see over there in this general area, there's a drawing so you can kind of see it. So on this side is a different type of target. This is the one that can spin, okay? And it's sitting on that metal piece like the other picture, but here's the target. And then over here is the filament inside of here. And so what happens is you're going to have amperage is going to come in. It's going to heat this up to boil off electrons. Applied voltage is going to push it across, and that's going to create the beam that's going to exit the tube, okay? So in order to know, there are two processes we are studying, two processes we need to study, okay? The first one is X-ray production. That is what's going to happen inside the X-ray tube. So when we're learning, we need to know, how do we produce an X-ray? The second thing we're going to do is learn image production. That's going to happen outside. It's going to happen outside of the tube, and it's going to happen at the actual image receptor that creates the actual image that we see, okay? So first we'll start with X-ray production. There are 4 things we need for X-ray production to happen. 4 necessary elements to X-ray production. Number 1 is an X-ray tube with a vacuum inside. I told you that already. Without the vacuum, you don't boil off electron, you get no electron cloud, you do not produce an X-ray. Must have a vacuum. Number 2, the source of electrons. Electrons are particles. Okay, so you have to have a source of electrons, and this is going to be a cathode filament. It's called the cathode. It has a filament on it, which is just a coil of wire. Okay, you have to have a method for accelerating the electron particles to a great speed. And in this case, it's going to be voltage. So amperage is going to create your electrons, and then voltage being applied when you push that button with your thumb is going to push and accelerate the electrons across the tube over to the target, which is known as the anode. So the method to stop the electrons inside the electron tube and cause the transformation and create those X-ray photons to make the X-ray beam is going to be the anode or the target. 2 things that mean the same thing. Okay, anode and target means the same thing. Okay. Now there is a second video that I am going to have you watching. It'll be within that same Wii video. These videos that you see in here, or at least this one, is created by a company that we use in the program that has animated videos teaching about X-ray physics and about the tube and everything and all the machines and everything. And so I learned very well from animation. So there are some that you can find on YouTube, and so we share them here in this. So you're going to have to watch that. So we talked about X-ray production, the 4 elements of X-ray production. That is to get the X-ray to come out of the X-ray tube. But then there is also image production process, okay? So if you remember, X-rays were discovered, not created, discovered in 1895. They existed already, but Rankine was a physicist back then, and he discovered these X-rays using something called a Crookes tube, if you remember. Okay, that was in 1895. So the process for creating an image and is happening in this drawings that you see on the right. You don't need to know the drawings for a test, okay? It's just there so that you can kind of follow along. So first, an X-ray beam energy is produced using high voltage electricity. That was the process we just discussed, okay? So in here, you see an X-ray tube with some lines coming out of it that represents the X-ray beam going through the patient and then striking a digital detector. So the X-ray passes through matter. Matter in this case is a patient or whatever you're X-raying, okay? Could be an airplane part, okay? And then strikes an image receptor. Now, an image receptor can be called an image receptor. It can be referred to as an IR, for image receptor. And it can also be called a digital detector. 3 separate phrases that mean the same thing. So when you're talking about that, you can call it the detector. You can call it a digital detector. You can call it the IR. You can call it the image receptor. It's all accurate, okay? And the IR, the image receptor, the detector, converts the energy of X-rays into an electronic data set. So now this is the language of digital. And that's something we're all familiar with, right? We all understand that concept, okay? So it creates a data set of signal values, okay? So signal is a data set. And then a computer processor converts the signal values into a viewable image, okay? So there are certain radiation characteristics you need to understand. So the first one is primary radiation. This is the X-ray beam after it leaves the tube and before it reaches the object. This is referred to as primary radiation. So if we look at this image, number 1 is showing you up here at the top. This is going to represent the X-ray tube, okay? And these wavy lines, they represent the useful X-ray beam, okay? So when the beam leaves the tube, we refer to it as primary radiation before it hits the object, and the object being the patient, okay? And then we have scatter radiation. Scatter radiation is a deflected X-ray that is exiting the object. It might strike the image receptor. It might go off into space. It might go towards the X-ray tech, right? But it is 100% non-diagnostic. It doesn't help at all. And if it hits the image receptor, it's just noise. It just contributes to noise. It makes it hard to see the image. So it's noise. That's called scatter radiation. And you can see here, number 4 is showing you a beam that has hit the patient, but rather than hitting the image receptor or going through or absorbing or anything, it just goes off into space. That is scatter radiation, okay? The next is absorbed radiation. So these are X-ray photons that absorb into the patient. They don't exit the patient. They hit a bone and they absorb, okay? And they are very useful. This is very useful radiation because it helps to create the image. At areas where the beam absorbs is what looks white on the image because nothing went through the patient. So nothing hit the detector. There is no signal data represented by that. So it looks white, okay? So we've got absorbed radiation, and you can see here, it's showing you a beam that came down, hit a part of the body, and just absorbed, okay? And the last one is called remnant radiation. So this is also diagnostic radiation. It results after the beam exits the object. So what have we got? We've got two types of diagnostic radiation. We've got absorbed radiation, that's going to make the white areas. And we've got remnant radiation, and that's going to make the black areas, right? So now we have an image. So if that radiation gets through and it hits the image receptor, it's going to make a black area and therefore give you the contrast necessary to create an image made of black and white. And yes, the images also look gray. We'll look at that a little bit and you'll get kind of an idea, okay? So here we've got the remnant radiation. The remnant radiation goes all the way through and doesn't hit anything that, that is going to absorb it, and it's going to go and hit the image receptor, okay? And the process of absorption is known as attenuation. Okay, attenuation. So absorption and attenuation, very similar concepts, but attenuation can be at any level. It can be a little bit absorbed. It can be very absorbed. Okay, so that's where we get the grays. All right. So attenuation is the loss of energy, of radiation energy, as a result of passing through an absorbing material, such as the human body. All right. Different materials absorb or attenuate radiation energy differently, based on the density of the object, like how solid the object itself is that it was hitting, and the atomic number, meaning that the higher atomic number that you have, the less likely the X-ray beam can get through it. It's more likely to attenuate, meaning absorb, right? So think about it like that. Okay, the example that I love and is to always compare an X-ray beam to light. Okay, so we're going to put that example in our head. If you hold up a brick and you punch the brick, 9 times out of 10, your hand is going to, the brick is going to absorb the energy in your hand, and you're not going to punch through the brick. Okay, it's going to absorb, it's going to hurt, and it's going to absorb the energy of your hand. But if you hold up a piece of paper, the energy in your hand is greater than the density of the paper. So you're going to punch right through it. Okay, you're going to go right through that paper. And that is the same thing with X-rays. Okay, they come out of the tube at different energies. And if the energy of the ray, the photon, which is another word for an X-ray, a photon, if that wave, photon means wave, if that wave is of greater energy than the atomic number of the object, the density of the object, then it's going to pass through it. If the wave is less, then it's going to absorb. Okay, and this is known as differential absorption. So when you take point an X-ray beam at a body, it has many different density objects inside of it. The density of a bone is very different than the density of a muscle or skin, right? And so, or air. And so it's going to give you differential absorption within the body. This is what helps to create the image. So the degree of attenuation of the body can be high or low. A high attenuation, meaning high absorption, occurs in a radio-opaque material. I think we all know what opaque means. It means you can't, we think of opaque, it's you can't see through it, right? So now radio-opaque means that an X-ray can't pass through it. Low attenuation, meaning low absorption, occurs in a radiolucent matter. What's a lucent object? That's something you can see through. So if it's radiolucent, it's an object that an X-ray can pass through. Okay. And I want you to listen to me really carefully right now, because it's important when you're learning these topics to think about what the body is doing. The body is an object that you can touch and that the X-ray photon can also touch, right? Whereas the image is something you're looking at. And you really have to differentiate that when you're thinking of this topic. You really have to think about what is happening in the body, what is happening at the tube, and what is happening at the image receptor or at the X-ray you're looking at when you're thinking about it, okay? So to be radiolucent means an X-ray can pass through it and it looks black on the film, right? So let's talk about those two words. So the image on the right is an X-ray of the chest. And what I want you to see when you look at it is that there are areas that are obviously bones that look white or some shade of gray and white, okay? So here we have clavicles, we have these ribs, right? Lots of these ribs down here. And you can see that there are differences between that and the black areas, which are the air. And then you've got the heart, which is almost completely white, right? And you've got the liver over here, right? And you've got the stomach over here. And so those areas that are very white are either bone or a denser object. Remember I told you we're going to talk about the object's density, right? Whereas the bone allows the X-ray to pass through a little bit more depending on the type of bone, a lot more than the heart does, right? And whereas the air lets the X-rays pass right through it. And so they look black on here. So to be radiolucent means to have low attenuation. And it is when the material allows an X-ray photon to pass through easily, like lungs or gas within the body, okay? To be radio opaque means to have high attenuation. It's a material that absorbs or at least reduces the energy of the X-ray. And examples of that in the body would be bone, or sometimes we use lead on an image, you know, to put our initials there or to label something. Another example of something that might attenuate is muscle. Maybe it doesn't attenuate as much as bone or the heart or something like that, but I guess the heart is a muscle. So it just depends on how big the muscle is, right? But the heart is also full of blood. So the blood itself also attenuates, okay? Fluid will attenuate in the body. If this lung was full of fluid, it would then look closer to white than it would look closer to black, which is a representation of air, okay? I'm going to give you guys a second to think about this and see if you have any questions or if you want to phrase it to me and ask me if you're thinking of it correctly, anything like that. This is your chance. Just interrupt me, okay? Tell me where you're confused.
Could dense also mean like thicker in a way? Is that or not really? Is because like the thicker it is, the more
Okay.
opaque it is and not letting it.
So attenuation. So the thing I want you to take from all of this is that an attenuation means it absorbs, it reduces the energy of the X-ray beam that left the tube, right? And it is something happening in the body. So we started talking about the X-ray tube, what was happening in there. Now we just talked about what was happening within the patient's body. Okay. And we're going to go through some actual X-ray images to show you what we're talking about. Okay. Oh, see, now I might have to annotate. I'm afraid to use it and have it not work. Okay, hold on. Let's see. Oh, like. Okay. So let's see if I use this. Okay. So on the left-hand side, you're looking at the X-ray of a knee. And on the right-hand side, you're looking at an X-ray of the abdomen and the pelvis. Okay. And they look very different. The one on the left has a lot more attenuation in the bone than it does in the surrounding muscle. So here we have muscle, and this is our bone, and you can see the patella here because it's increasing the thickness, so it looks a little whiter here than it does in the surrounding bone because there's two bones, one in front of the other. In between here, it looks blacker because that's like a space of soft tissue. The skin is actually out here, but you can barely see it because in this X-ray, they've kind of the beam was more powerful than the skin. And so you really don't even see it out there. You probably see it better on an actual high definition monitor. But let's go with what we see. So this is what different patterns you're going to see on, say, an extremity. Okay. You're going to have muscle, you're going to have bone, and you're going to have skin. Versus when we come over here to the abdomen, and in this case, we're going to have some ribs. We're going to have these vertebrae across here. You can kind of see the way the bone looks there. There's a pelvis over here. So we have basic bone attenuation. It looks a little bit different than the knee because it's the thicker bones, okay? But then we have this sort of these gray areas where you can almost see, look, this is actually a kidney. And if I can remember how to take that back off, you can see that it has like a black surrounding the edge of it. And what happens in the abdomen is you have many different soft tissues, and each organ, these soft tissues, has a little bit different density depending on what type of cells it's made up of and whether it has blood in it and how large it is. And so you're going to have these much more subtle differences that are visible or not visible in the abdomen than you see in the differences between the bone and the muscle in the knee. So you have these differential attenuation patterns. And so you can go, okay, what's the language that we learn? How do I get rid of all this? I want to clear it all. They're all drawings. So lucent versus opaque. So we can say that the pelvis is fairly radio opaque. It absorbs. It doesn't allow all of the X-rays to pass through. Whereas over here, this gas in the bowel looks very black because the air inside the bowel or the gas inside the bowel lets the X-ray pass through much more readily. And that is also true here in what is probably maybe the stomach, or maybe this is the stomach and the other one is the large intestine, okay? And so that gives you this differential attenuation versus what you see over here, okay? Come on. There it goes. We can also use the difference in attenuation or the concepts of lucent and opaque when we're looking for fractures, okay? So on the left-hand side, this is a normal hip. The common site of fracture is going to be, well, let me get back my annotation here. So common site of fracture in a hip is going to be somewhere here, along here, or here in the neck, or somewhere here at the base right there. So those are the common site of fractures. So, but what we can see when we look at this is we have kind of like an even attenuation pattern all the way across, okay? And if we look at the edge of the bone, it's pretty solid lined. We don't see a break in it anywhere, okay? Now, in the center, we see a very, very greatly displaced fracture of the hip. You can actually see this lucency here like look right here, compare that to here. And that what has happened here is it's broken into two pieces. So you have the fractures happen along here and it's displaced and it's the bone is moved and this one's angled. And so that it comes this way and then the other piece is over here. This is obvious to look at, okay? It looks very different than the image on the left, much easier. But what's harder to find is the very subtle fracture lines. And when you do that, you look for lucent lines in the bone. And so here, the fracture line is right here. So here, this bone is not, it's not displaced. It hasn't gone so greatly apart, but it's unstable, meaning that it's a subtle fracture line, but if a person were to walk on it, it might turn into the hip in the center. But finding fractures, you really have to understand that concept of lucency, where you should not see lucency. That helps us to find fractures in an X-ray. Do you have any better, what do we think, Professor Friedman? Is that a good explanation? Is there a better way to explain that?
No, I think we're trying to explain the concept of it. So
Weird. Somehow I don't hear you, despite the fact that your mute is off.
weird. How about now?
Uh-oh.
Poor internet connection. Oh, no.
Is
Wait, you
anybody
can
else
hear me?
able to hear her?
Karen says she can hear me.
I can hear her just fine.
Yeah, we can hear her.
Weird. Okay. Well, let me
You
just
all can hear it, but I can't. Okay.
So the
Wonder if it's
density
got like
of the normal hip, you can see that the bone is homogeneous.
Oh, I gotta
So
fix
as
that.
you can see, it's
If you
all
guys can hear her, I'm gonna let her do an explanation while I try to fix that problem.
okay. So you can see the bone is clearly kind of like the same gray color throughout. But then here, for the non-displaced fracture, you can see that it goes from gray to black to gray, where, oh,
Did I change it up on you guys? I'm sorry.
yeah. Do you want me to share my screen? Okay.
Oh, I hear you. I'm sorry. Okay.
No, that's okay. So wait, I need to go to the hip. Okay, so as you can see how that lucency, that black line means that there's a disruption in the bone. So that's what radiologists are looking for, a subtle disruption in the contrast. That's why it's so important that we take good X-ray images that are exposed properly for radiologists to make a diagnostic image.
Perfect. Okay.
Okay.
Do you want to just keep sharing and I'll just follow along?
Sure.
Okay, so we'll go to the next one. Okay, so here you're looking at an example that has each of these are x-rays of the hands, and looking at them immediately, you can see they're very different. The image on the right is what most people's hands will look like on an x-ray. It is a standard pattern of, like we looked at the knee, and so it's going to have an attenuation pattern very similar to all extremities. But in the case on the left, one of two things has happened. Okay. One is possible that the person used too much technical exposure factors. They set the settings on the machine too high with too much power, kilovoltage, and it just blew right through the bones. Remember, I was telling you that if you set your factors so high and you make the beam too powerful in comparison to the object, it's going to have very little attenuation because it's going to be more powerful than the object. But in this case, what's actually happened is the patient has a condition called osteoporosis, meaning that this patient's bones are less dense. They are losing density. And so by losing density, when we give this patient the same amount of radiation and technical factors that we gave to the patient on the right, it blew right through their very porous, very less dense bone. Okay. And so in this case, the low attenuation on the image, meaning that it was more powerful and it passed through, is actually going to tell the radiologist that there is a pathology to the patient's bones. Okay. They're going to say that it has the appearance of osteopenia or osteoporosis when they read it. So sometimes the way that it looks and the changes in attenuation pattern from what is considered normal also keys the radiologist into a pathologic condition. Okay. So I keep referring to technical exposure factors. Okay. So these factors are referred to as the prime factors of exposure technique. So we've talked about the job of an X-ray tech, and the obvious job of an X-ray tech is to position the patient for the image. That's number one. The second thing is to choose technical exposure factors. Okay. So we talked about the X-ray tube, and we talked about the fact that we are going to apply amperage. Okay. And that's going to create an electron cloud. Okay. We're also going to choose, and so in this case, we're going to use milliamperage, and we'll get into what that means, milli. So we're going to choose MA, milliamperage. We also need to choose the time in seconds. For how long are we going to expose the patient? Okay. When you put those two together, and that's going to be our first math problem when we get there, it's going to be we call it mass. Little m, big A, that's milliamperage. And then the S represents time, and that is seconds. So you put them together, we call that mass. The next factor that we use is kilovoltage peak, so voltage. I told you that when we apply voltage to the tube, it's going to push the electrons across the tube to hit the target. So that's our second exposure factor, the voltage, or in this case, we use kilovoltage. Okay, it is referred to as kVp. So mass and kVp. So amperage, seconds, or time, and voltage. The next factor that is very important is source to image receptor distance, or SID. This is from the tube to the image receptor, whatever that distance is. So this is called SID. So mass, kVp, and SID. When you go into the program, these are the things you need to learn about in order to go and expose somebody. So you learn how to choose each of these things for each X-ray that you do. Now we are going to get much more heavily into those three things, especially when we get into the math. But first, I want to talk about the image receptors a little bit. We're going to go through image receptor types of systems. Okay. So we're going to talk about 4 different systems, but there are 3 types, just to be clear. So when Professor Freeman and I first started learning, we learned on a system at the college called film-based radiography. And when we first started, the local hospitals were not using film anymore, except in mammography. So we learned on film. We learned on computed radiography. That's the next type. When we went to the hospital, we used both of those. Okay. So film-based radiography, computed radiography, or CR, uses a photostimulable phosphor technology, or PSP. They were cassettes, okay? Film-based used a cassette with film in it. CR used a cassette with a PSP inside of it, okay? It was a storage phosphor technology. But the more modern systems use direct conversion, DR, which uses amorphous selenium, or ASE, or indirect conversion, DR, which is digital radiography, which is using amorphous silicon, or ASI. These systems will generally require no modification to a standard radiographic system. You actually can take a system from 1960s and you can use any one of these if you have the right plate, okay? So there are obviously newer machines that are just built directly as DR, which is digital radiography, or digital radiography. That's the modern system. That's what you're going to see in most places where you go now. And that is what we have in the lab, okay? But you can use really old machines with all of this technology, okay?
Just to clarify, Professor Windmiller, so you're saying like an X-ray tube from the 1960s, we can use any of these types of plates in order to create an image?
Correct.
Oh.
Correct. Because all that each of these plates have to be exposed to is an X-ray. So it doesn't, you could use a Crookes tube X-ray, okay? And it would maybe it would be powerful enough to be picked up by these, but any type of X-ray can hit any one of these receptor systems and create an X-ray image.
So pretty much the medical advancement wasn't so much in the X-ray tube, but more so in the image plate technology.
You're right. And if you think back to the first time we got together, there was something I said at that time that referred to that, which is that the exact properties of an X-ray that were discovered in 1895 by Rankin are exactly what they are right now. There might be advancements in the machinery, but the properties of X-ray and the concept that an X-ray hits a plate of any type has not changed the entire time, because it's a basic physics property. That's why we discovered it. We didn't invent it. And so it can't change because it's basic physics. Whereas the technology that we use to create the image, the receptors, they can change over time and will change over time.
Okay.
So to be clear, we're going to talk about film and CR, but I want you to know that the ARRT who does the tests to become a technologist. They don't test on film anymore and they don't test on CR, but we're just going to talk about it so you at least know it. Okay. We all know the concept of digital versus analog, right? We've got our digital phone, or we can just pick up a telephone, right? Digital versus analog. So film base is an analog cassette system. It is just a cassette that you put a piece of film in, okay? And some of you may have even have done photography that has actual film inside of it. Same concept, okay? In the case of photography, it's a piece of film that gets exposed to light and then is able to create an image. But in the case of a film-based radiography, it is a piece of film that is sensitive to X-ray that then creates the image. And then it's that piece of film is developed in a dark room. And there was still a dark room up until this last year at the college. We literally just rebuilt that lab. And so that dark room it's actually there. There's just not any equipment in it anymore to create an image in it. But we worked in dark rooms when we first started learning and exposed the whole bin accidentally. And when we go into the lab, we'll show you the pass box where you actually would be able to pass films back and forth between like a room and the dark room. Okay.
I can still remember how the chemicals smell.
So wild. Yeah. So strong. So we'll go to CR, which is the next slide. So computed radiography was the next development that happened, and these new cassettes were created. You can see the image on the bottom in the middle. That is an example of someone opening up that cassette and showing you the piece that you can pull out. And so it essentially was a storage phosphor technology plate that was erased. So you would take an image with it, you would put it into a reader. So you can see the woman at the top, she's putting it into like a single feed reader. And it would pull out that piece and it would read it and then erase it and then put the piece back into the cassette and you would pull the cassette out. There were also readers that could do multiple at a time on the right. And then there would be a monitor hooked up to it where you could see the image coming up and you could check it and make any adjustments you needed to it. So this is CR cassette with reusable imaging plate. There was a reader and then there would be a monitor. We literally just got rid of those too in the lab. And up until 4 or 5 years ago, we still had these at the hospitals. We didn't use them necessarily. They were kind of like downtime usage. But we finally trust our DR plates, enough of them to not go take the whole hospital down if they're not working. So this is all the straight DR just happened in the last, just solid switch just happened. And we just upgraded the lab into a solid DR. So modern image receptor systems. So we talked about film. CR is technically a digital system, though it isn't a true digital detector because it's an erasable plate, right? And so you're going to switch from a CR erasable plate to a true detector. And a true detector is made up of a matrix of pixels. And what I want you to understand is called the TFT array, okay? Which is, trying to remember at the top of my head. Thin film transistor array. So imagine if you had a pixel, think of it as a little square. We're going to look at an image of it, but it's going to be a little square. And then if you took a whole bunch of them and you drew them into columns and rows, right? So let's just imagine there's going to be millions of them, but imagine if you had 10 of them. You could have 2 across for 2 columns of 5 or something like that, right? And so that would put together, each of those would represent a detector that could pick up on a signal, and that would help you create the image. Okay. So there are 2 types of DR. There's going to be a direct DR. This is direct conversion. And what this means is that an X-ray photon is going to hit the material inside of this photoconductor, and it's going to be amorphous selenium, and it's going to take the X-ray photon. It's going to then transfer electrons across the photoconductor to the TFT array, which is the pixels, and that's going to make up the digital signal. Okay, it's going to give a readout that way. That is direct. The reason we call it direct is that there is no light involved. Whereas within an indirect conversion, and this was true of CR and DR, so indirect conversion, it's going to scintillate, meaning that the X-ray is going to hit the scintillator, and that means scintillate means to create light. And then the light pattern is going to strike the photodiode made up of amorphous silicon, and then the electrons will pass across. No, the light will be conducted down, and the light will strike the TFT array or the detector. So essentially what you've got is a direct conversion means that the pixels, the TFT array, they are X-ray or electron sensitive pixels. They read out based on what electrons hit them. A amorphous silicon is going to be, or the TFT array involved in indirect is going to be light sensitive pixels. So one reads electrons striking it, the other one reads light striking it. So it's indirect because it has to be converted to light first. So X-ray turns into electrons, goes to the detector. Indirect, and indirect, the X-ray is turned into light, and the light strikes the detector. So indirect. Okay. And there's going to be a readout from that. And then it's going to go from an analog to digital converter to create something that you can see in an image. But we're not going to get into that in too much detail in this chapter. So, sorry, we can go to the next one. So image receptor systems use solid state electronics and thin film transistor technology. This is the IR, image receptor for digital. The detector permanently is encased in a rigid cassette. It's called a flat panel detector. The radiation exposure to the detector creates an electronic signal proportional to the exposure, right? So we talked about what was happening in the body, attenuation. So if you have, I want you to think about this very clearly. If you have high attenuation, that means no X-ray reaches the pixel. So it's got low signal. There's low exposure, low signal. But if it's not attenuated in the body, then X-ray is going to hit the detector, right? And in that case, you've got low attenuation, very high signal, high exposure to the detector. You've got exposure to the body and exposure to the detector creating signal. There's no reader required for this digital technology, this DR. Okay, the image is able to be displayed in seconds. And then we talked about it. There are two classes of DR technology, indirect and direct. So I want to go back just to that list. If you don't mind, we'll go back a little bit to that first list. So in this list, we've got three things we refer to in the department: film, CR, and DR. Because even though now you're learning about like direct versus indirect, there is no, that doesn't mean anything when you work in the department. You're either that's happening on the inside of the detector. You're not, that doesn't mean anything when you're there. So that's just about how it's made. So really, when you're working in practice, you're either working with film, CR, or DR. And so basically what we have in the lab is DR. That's what you're going to see when we all go to the lab together. And when you go into your sites, the chances that you'll see anything other than DR these days, I can't even think of anywhere that still has cassette based, unless it's like a clinic or something like yeah, I'm not even aware of anybody having, I mean, I don't know if you can think of anybody.
Maybe a small independent clinic.
Yeah, maybe a small independent clinic might have CR. Nobody has film. Sorry, we can go forward again. Good. So we're going to finish up before we get to the math, and then we'll take a little bit of a break. So give me a couple more slides, okay? Okay, so I want you to go back to what I told you. So the detector is made up of hundreds of thousands of pixels. They're minute, okay? We're talking about like millimeter sized pixels, okay? And so it's going to be an array a matrix of pixels. So let's talk about these. Pixels is a word that relates to digital technology, but actually when we're talking about them in the detector, we call them detector elements or DELs, DELs. Okay, so I'll go from the word pixel to detector element. Okay, but know that I'm saying the same thing. All right. So exposure or X-rays that reach the detector element, each of them, create a stored electronic charge. Okay, depending on the amount of exposure that reaches them. So charge values are analog and are directly proportional to the exposure. So I want you to think of it like this. They're going to have a number, okay? So let's imagine that the number is between 1 and 100 or 0 and 100. So if nothing reaches it, the number might be 0. And if the strongest ray possible hits it, the number might be 100, but it also might be 50. Okay, it might be somewhere in between because the beam itself is polyenergetic, meaning that it has rays of different energies in it. And so different energies may reach it or nothing may reach it, or, and so it's not always going to be identical. And that's how we create the image. The analog signal is converted to a binary, meaning the number I'm telling you about, digital value for processing. Okay. So it has to go from exposure and then it becomes a number. And that is the converted to a binary, a number. And that's the digital side. So it's analog to digital conversion, X-ray to digital conversion. Okay. And then the digital signal, remember, signal means data. That's the data. That's the digital representation of digital data signal is analyzed by a computer. So it's going to go, okay, let's imagine it's 1 million pixels or detector elements. I've got 1 million of them. And tell me what is the number on each of them, right? And it'll take that data in. Okay, each of them has a number, and it's gonna create what is called a histogram. A histogram is rescaled to optimize its appearance because we want it to look a certain way. It's going to go, okay, this is the exact representation of the data I got, but I also know that I need it to look a certain way to make it diagnostic, and it's going to adjust that based on each one. So there's going to be a little algorithm saved in the computer for each type. So if you tell it like, this is meant to be an abdomen, this is meant to be a chest, this is meant to be a knee, it's going to make an adjustment to make it look closer to the contrast and like signal value, meaning light versus dark, that it should be. Brightness is the word I was looking for. So it's going to adjust the brightness and the contrast to kind of match what an algorithm of expectation for that particular body part. Okay. These are called lookup tables. Okay. So let's just look at indirect and direct again. I was kind of explaining it, but this is a better image of it. Okay. So indirect DR systems use a scintillator, meaning scintillate means to emit light. A scintillator material to capture energy from the remnant X-ray beam. Remember remnant? That's what left the patient. Okay. So it's going to capture the energy of the remnant ray and scintillate. So it's going to emit a light proportional to the exposure. The light is captured and converted to an electronic signal. And there are 2 methods of signal capture in this indirect. One can be a charged coupled device or a thin film transistor, which we already looked at. Thin film transistor layers are made of amorphous silicon, and then the output is digital. Okay. And then we'll go over to the next slide, which has our direct. So direct DR systems do not have a scintillating layer. Okay, so we're looking at a pixel array now, okay, or a detector element array. So remnant X-ray beam energy acts directly with the TFT layer to create an electronic charge. The TFT layer is amorphous selenium. The output from the TFT layer is a digital format. I invite you to read the chapter, okay, because my explanation might make no sense to you. So please read the chapter. It actually reads quite nicely in order to understand this, because this is a difficult subject that, like I'm telling you, this entire lecture you're getting is taught in one class. So understand that like the way I'm explaining it to you is a new topic. So you need to read it and understand it in different ways other than just what I'm saying to you. Okay. So to just cap off what I've been telling you, and then we'll take a little bit of a break. We're going to talk about the units of measurement in the SI units, which is the Système d'International units. So basic ones that we need to know in order to do this chapter are the basic units of energy for an X-ray tube are the big A is an ampere, it's energy current. Okay. And the basic unit for energy strength is the volt. The basic units of measurement are M for meter. This is length measurement. And also S for second, measurements of time. So note that the A and the V in ampere and volts is written in capital, and the M and the S are written in lowercase. It's important that you differentiate this when you're writing out these calculations, because when something is big or small can change its meaning. So it's important that you pay attention to that. And then I want you to understand what the little m, little c, and little k means. We talked about kVp. So m means milli or thousandths, 1/1000th, or 0.001. Right? So a milliampere is 1/1000th of an ampere. C for centi is 100th, or 1/100th, or 0.01. Okay, so smaller than 1. Both of those units, milli and centi, are smaller than the number 1. And then K stands for kilo or thousand, meaning 1,000, right? Not 1/1000th, 1,000. So in voltage, we do kilo. So we are using thousands of volts in an X-ray. Thousands of volts in an X-ray. Okay. Other forms of medical imaging can use megavolts, and that's more like for like treatment and stuff. We don't use that in basic radiography. Okay. The garden hose analogy says that let's imagine a situation where you have a garden hose hooked up to a spigot. So the amperage is going to be the volume or the current or the amount of water moving through the hose. Bigger hose, more volume. Okay. So that's how many water droplets are there. Compare that to an X-ray tube. How many electrons are moving across? So amperage controls quantity or amount. Whereas voltage is the pressure or the quality or the strength. All that means the same thing. Pressure or quality or strength. That is the amount of pressure in a garden hose analogy. It's how far you turn it, right? So you turn up your spigot, more you open it, the more power it has behind the water. That's going to be similar to voltage. So the more strength or quality or power behind is the voltage. So you up the voltage, up the kilovoltage, then more power there is to the X-rays you're creating. They're more powerful. Okay. I think there's only a couple more before we take the break. So actually, if we could take a little bit of a break to let our brain settle, and then we get to this, it'll go with the math better, the next couple. So we'll take 5 minutes. We'll come back at 6:08.
Okay, see you all back at 6:08.
Okay. Okay, we're back. So hopefully all of you are paying attention again very closely.
Does anybody
Before
have
we
any
get-
questions so far? I know this is very intense subject matter. And we've already gone through a lot of information. All right, you guys got it. There'll be a
Solid.
pop quiz at the end of
Right
this.
now, pop quiz. All right, everybody get ready. You're logging in right now. Pop quiz on it.
Just kidding.
Okay. All right. Is it easy to reshare, or you want me to do it?
I can share.
Yeah, because you're going to take over, so it's probably better. Well, I'm not, I'll do the last couple and then. Okay. So we are back to talking about radiographic image quality. Okay, so we talked about the tube. We talked about what happened in the tube. We talked about that was X-ray production. Then we talked about attenuation. That's what happened in the body. Now we're talking about radiographic image quality. We're talking about what's happening in the detector and the image that we're looking at. Okay. So optimum image quality is a function of X-ray exposure and image receptor characteristics. So there's many factors that actually go into the quality of the image. Now, quality I referred to already as the strength of the beam. That is not what this means. Quality literally just means how diagnostic the image is. Okay. And so you have the two main factors, which are going to be image signal. So exposure turns into a digital signal that represents what was in the body, and then image resolution. And there are many types of resolution. And resolution is, it has many different ways we can talk about it. Okay. So the primary image quality factors are signal value. That's the critical factor. Okay, signal value factors have to do with image receptor exposure. So what attenuated, what didn't attenuate, what reached the detector, and then contrast. Okay, so contrast has to do with the contrast, probably in this case, of the body. So what is the difference between the objects in the body, between bone and soft tissue and gases and airs and all that kind of stuff. Okay, and then image resolution factors has to do with two types of resolution: spatial resolution and contrast resolution. Now, spatial resolution is going to have to do with how sharp the image is, and we'll get into that. Or contrast has to do with how well you can see the difference between two tissues that are next to each other. So image brightness, how bright it gets, how white it is overall, how dark it is overall, and contrast is pretty much controlled by the display monitor. We can adjust that as long as we gave enough exposure to the patient for the particular object. We can adjust that on the monitor. So it's not something we talk about as much anymore. So image signal value is determined by the total X-ray exposure to the image receptor. It is directly proportional to the X-ray exposure, meaning if the exposure that reaches the detector is high, then the signal value will be high. If the amount of X-ray exposure that reaches the detector is low, then the signal value will be low. Okay. So optimum image receptor exposure affects the visibility of the resolution, how well you can see it. Okay. So if not enough reaches it, it's going to look noisy and you won't see the object as well. Suboptimum exposure, meaning not enough exposure to the patient, creates something called quantum model on an image. And our model just means noise. Okay, it's not contributing to the diagnostic quality of the X-ray. So essentially, one of the things that we're going to learn about in chapter 9 is the concept of radiation protection. A lot of people think, well, we said ALARA is, we want to keep the dose as low as reasonably achievable because that line is where it's diagnostic. Once you go below an exposure diagnostic level necessary, it's 100% unnecessary radiation, right? It's like, if I don't give you enough of an X-ray dose to get the image I need, then I gave you 100% useless dose, right? It didn't create a diagnostic image, okay? So I'm not going to get into detail into this because this is going to get into a lot of stuff that's from the second half of the chapter. But just be aware. So exposure is affected by mass, milliampere seconds. Beam quality is affected by KVP and beam filtration. Patient characteristics can affect how attenuation occurs. So think about the tissue thickness or the tissue composition, like what cellular makeup does it have, or the pathology that might exist within the body. Distance, we're going to look at distance in a math problem called the inverse square law. Radiographic grids are part of this mix, so it's going to be the grid ratio can affect the image. X-ray beam modifications Okay, so how the field of view that we create, or whether the object or the tube is tilted. And then image receptor characteristics, that's the way the actual detector was created by the manufacturer. So fill factor and sensitivity, which is nothing you're going to be able to control because it's going to be what it is that you're using. That's just not controllable. Okay, so good signal value is the combination of all of these variables being optimized. And that's where the difficulty comes in the program, because you take an entire semester of just learning about everything on this one slide and what every single one of those means and what you can adjust and what you can't. And the guy that teaches it, the professor, will create these huge grids of this information and be like, okay, if this one goes down, what effect does it have on the other one? You know, it's difficult, but great way to learn.
So each of these variables has a different relationship with the other. So if one changes, then you have to see how you need to adjust the other factors in order to get a good diagnostic image. So everything has a relationship to everything else, but if you change one, you have to see what the cause and effect is.
You know, sometimes you use them on purpose. Like you might say, I'm x-raying a child and they're moving. And so I really want to reduce the amount of time, you know, the seconds in the mass. But by reducing it, I have to either bump the milliamperage, and if that's not enough, I might have to change the kilovoltage, or I might need to decrease the distance, or maybe I want to make the image sharper, so I decrease the distance, but I still have to give the patient the same dose, so I need to up the mass. So you have to make these changes because you may choose to change some of the factors to improve one thing about the image and then make the adjustments to make sure that the patient still gets the right dose. Okay, so take your brain out of the digital world for a second. These are photographic images. So remind yourself, photography film, okay, or photography, okay, has to do with light. It's light, okay? So when we talk about photography, there are different quality photographs of the gravestone. On the top left, we are looking at an image that is too dark. On the top right, the image is too light. On the bottom left, it's blurry, it's out of focus. And then on the bottom right, the image is just perfect because it is a balance of good exposure, light exposure, contrast, okay, and detail in the image all make up a good photograph. Okay, we'll go to the next. Okay, so we are going to switch up here. A lot of the stuff we listed a couple slides ago, that long list of factors we get into in the second half of this chapter. We're going to go ahead and I'm going to sit back and we're going to get into the math. There are many different types of math that we go over in the program, but we're going to just stick to 4 formulas for the purpose of our class. And I'm going to step back and let Professor Friedman talk.
And if anybody needs to interrupt with any questions, or if you guys need a clarification on anything about details or anything, go ahead and type it in the chat or just interrupt. So we're talking about milliampere seconds mass. So again, it's a milliampere, which is the amount of exposure multiplied by the time, which is measured in seconds. It's the primary factor of image receptor exposure. Mass represents the quantity of X-ray production. So again, just like that garden hose theory, the amount of X-ray production is the same as the volume of water going through the hose. It has a direct relationship to X-ray exposure. So again, the higher the mass, the more exposure there will be more dose, a higher dose. So higher, which will also mean a higher signal value. So let me just say that again. So the higher X-ray exposure will have a high signal value, but will also have a high dose to the patient because you have more quantity of the X-ray beam going towards the patient. And again, it's just calculated by the simple multiplication of MA, milliampere, and time, which is measured in seconds. MA times seconds gives you mass. And that's a key concept that we will utilize all throughout radiology. Whenever somebody asks you your technique, they're going to say, what's your kVp and what's your mass? So mass and IR exposure. So as you can see through these three radiographs, radiograph A, they only used 5 mass. As you can see, it has low attenuation. So not much, is that correct, Cindy? Okay. So not much of the X-ray beam is going through the patient. It's not reaching the image detector. So it's very bright white. So those X-ray beams are not going through the patient, reaching the image plate.
So high attenuation, yeah.
So high attenuation. That's why it's so bright and so white. And it's very difficult to make a diagnostic result out of this image. But if you double the mass, it doubles the exposure. So you can see more clearly the detail and the contrast. So you can see the difference between the white areas and the black areas, the areas of high attenuation and the areas of low attenuation. But then again, if you double that mass again, which means you're doubling the exposure, so you're using twice as much technique, then you're burning everything out because you're giving it more quantity of those X-ray beams to go through to the image receptor. So now everything's getting blasted. So again, you increase the exposure, which means you're also increasing the dose to the patient, which is low attenuation. Because all the X-ray beam is going through to the image plate. Everybody following? Okay, so here's the first math problem, and it's just to calculate mass. So here we have 200 MA, milliamperes, and we want it at 200ths of a second. Yeah, that's hundredths of a second. So we multiply 200 MA by 0.02 seconds, which will give us 4 mass. That's our technique, 4 mass. But if we double the milliamperage to 400 multiplied by 0.02 seconds, it'll give us 8 mass. So that's double the technique, double the exposure. Regardless of the MA and time combinations, the same mass value will yield the same exposure, which is also called the mass reciprocity law. So what we're saying is, if you want to have the same exposure, which is your technique, 16 mass, as long as you use combinations of MA times time to equal 16, and it doesn't matter which combination you use, as long as it equals 16, you'll still have the same exposure.
So like, again, as I had mentioned earlier, you think of the wiggly child. Okay. So if you need to shorten the time, and so you shorten it so that you get a better resolution with less motion on the image, you're going to need to boost your MA to get the same. You still have to use the same exposure on the baby, but you're going to adjust it to get what you need.
So just again, to reiterate what Professor Windmiller was explaining. So say we had a wiggly child and we had the original technique that it gave us was 8/100ths of a second, but we wanted to make the exposure as quick as possible. So we shortened it. We shortened that time, but we still wanted to keep the same exposure because it was a good image. So we cut the time in half, but in order to keep that same exposure, we had to increase the MA in order to keep that same exposure. So from here, we decreased the time, and then we had to up the MA, milliamperage, to keep the technique the same, the exposure. So calculating mass requires you that you convert fractions to decimals. So everybody knows how to do that. So 100 MA times 1/10 of a second is 10 mass. So you convert the 1/10 of a second to a decimal by dividing 1 by 10, because it's 1/10 of a second. So 1/10 of a second converts to 0.1. So 0.1 seconds. That's your time conversion in a numerical value. So 100 MA times 0.1 seconds gives you 10 mass. So whenever you're calculating mass, you'll always want to convert your fraction to a decimal in order to calculate mass easier.
Yeah, I mean, if you want to make it 100 over 1 times 1 over 10 and then cross multiply, you can go ahead if that works for you. But it's easier if you just convert it and go the other way. Yeah.
Patient factors.
So the patient and their tissue characteristics, I mentioned this before, can greatly affect signal value. So I want you to think of it the easiest way possible. So it can be a difference of subject density, so the object. So tissue thickness or tissue composition. So let me give you a couple of examples. Imagine you have a 10-pound baby and you want to take an image of the chest, but then you have a 30-pound baby and you want to take a different an x-ray of that baby's chest. So tissue thickness difference, okay? Versus tissue composition. Okay, I need to take an image that's going through the liver. That's much denser. It's a different tissue composition than the tissue of the lung. Okay, so tissue, this is subject density. So density refers to the object. Density has nothing to do with the image. When we say density on an image, we are referring to something else, and we don't use it when we talk about digital. Stay away from the word density when you're talking about the image unless you are referring to something in the body. So tissue thickness versus tissue composition. The other thing that can happen is a contrast material difference having to do with pathologic conditions. So imagine having to take an image of a patient with a nice set of clear lung. It's mostly made up of very light tissue density and air, versus a patient who has pneumonia and their lungs are full of fluid. It's going to be very different composition. So pathology can change your patient factors. So the patient's factors can also affect the image. So signal value and subject density have an inverse relationship, meaning that as the subject density increases, the signal value will decrease. So inverse relationship. As the subject density increases, the signal value at the image detector decreases. So inverse relationship, okay? And we'll go.
So now we're going to talk about KVP, and KVP is the quality of the beam. It's the beam quality. KVP controls X-ray beam penetration, so the strength. So again, back to that water hose theory, it's how fast the water's rushing out of that hose, how high you've turned on the pressure to that water hose. So it has a direct relationship to signal value. So the higher the KVP will be, the higher the signal value, which will decrease density.
So to say that it's non-linear, so earlier she was talking about the linear relationship of signal value and mass, meaning that if I double the exposure, I'm doubling the signal value, and it will continue like that infinitum, doubling, tripling, whatever. But with KVP, It's not a linear relationship. It's going to go up by 15%. So we have to have a calculation that explains this to us because it's not going to be direct. You're going to double one, it's going to have a different impact on KVP. Okay, so it's still going to go up, right? But it's not a linear relationship. It doesn't follow along two solid lines together. Okay.
So the X-ray beam is heterogeneous, which means it has different strengths. So as Professor Windmiller was saying, there's a 15% rule. It's a calculation, it's a formula that we utilize to help us calculate what technique we should use. So by increasing the KVP by 15%, it will approximately double the image IR exposure, which is the same thing as a signal value. So if you increase the KVP by 15%, it will double the signal value. It will double the exposure. It will make the image twice as dark. If you decrease the KVP by 15%, it will approximately half the image exposure. So it'll decrease the signal value by practically half. Let me see if I can do the whiteboard. Okay, so 15% rule. So say you say your technique is 80 kVp and your technique is 50 mass. But the image that you took is too dark. So, and it's really way too dark. So what you're going to do, what you want to do is you want to decrease your KVP see you guys all over the place. It's weird because I can't see my cursor. So 80 kVp is your original technique, and you want to decrease your exposure by half, which means you need to decrease the KVP by 15%. So what is 15% of 80? The easiest way that I do it on the fly is, what's 10% of 80? 10% of 80? 80 is 8. What's half of 8? Is 4. And then 8 plus 4 is 12. So 15% of 80 is 12. So in order for me to decrease the exposure, I have to decrease the KVP by at least 12. So at least, what's 80 minus 12? Is 58. Is that correct? Oops.
$68.
68, my bad. So it's 68. So decrease. I see everybody's names going everywhere. So to decrease the KVP by 15%, which will mean it will decrease the exposure by half. And then, so if I say the opposite happens, say I want to double my exposure, now I know I will need to at least increase my KVP 15%. So now it'll be 80 plus the 12, which will equal 92. Oops. So at least 92 kVp.
Oh,
I don't know who did that. I didn't do that. Or did I?
I don't know.
Okay. So that's the 15% rule. So that's the easiest way that I do my calculations. So if I have a KV, if I have a set technique 80 and I know I want to change it, I say what's 10% of that original number and then what's half of that 10%. So which will give you the 5%. So 10 plus 15, well, 10 plus 5 will give you the 15. So 8 plus 4 will give you the 15% of the 80.
And this is a
Thumbs up
concept.
if you
The way
follow.
that this gets applied is has to do with something called it's about exposure maintenance. So imagine a scenario where you want to keep the same exposure, but you want to change your KV, or you need to half your mass. So when we do the math problem with it, it's like you're adjusting one for the other. We talked about the adjustment of MA in time, how you could maintain your mass by, let's say you wanted to lower the time, so you need to up your MA. In this case, you're needing to make a change in the KV up or down, and you need to know what to do to the mass so that the exposure stays the same, but you're changing. So instead of MA and time changes, we're doing mass and KV changes. So that's what we're going to see in the slide when we come back is the how to make an adjustment with this concept. So she's showing you like, okay, what's an easy way on the fly, because you don't have a math, you can't sit there and do math like on your, necessarily like in your head, right? You have to do it in your head on the fly. So she's showing you like how to quickly find 15% or up or down. And that's a great way, is the 10% methodology. Yeah.
Just break it down into easily manageable chunks.
Correct. Yeah.
So, and again, as
Oh, it's
Professor
not, sorry, it's not always going to be 10% of whatever the KVP.
It's always going to be at 15.
It's
And so she
15.
was just showing you like how to find, it's hard to do math in your head at 15. So she's saying it's kind of like how you find, like what's the tip. So you start with 10%, and whatever you get there, you take that number plus half of the first number you got, and that makes 15. It's a shortcut to
Well,
find 15.
what does the 68 represent? What does the 92 represent? Like the minus and the plus.
KVP.
Okay.
So the original technique was 80 kVp mass. And so the reason why we use the 15% rule was because the exposure was, let's say the exposure was too dark. And so we want to reduce the exposure by half. So we know we need to in order to do to have any sort of effect, you have to at least adjust the KVP by 15%. So that's where the 68 and 92 come from. So if you add 15% of 80, which is 12, then you'll get a higher exposure.
This is ridiculous. I'm sorry, guys. I need
Keep
like a
everybody entertained.
pencil or
So
something.
we're always going to have two KVPs.
No. I'm going to
you're
show you this. So we started off at 80 kVp and 50 mass. So what we really want to do is, let's say we need to make it 25 mass. So what did we do to the mass? What did the mass do? The mass went down by half. So if the mass went down by half, then the KVP needs to go up by 15%. So what is 15% higher than 80? What is my new KVP?
92.
92. Okay. And when we get back to the example, we'll see an example there. But it's just a general concept that they have an inverse relationship. So if the mass needs to go down, then the KVP needs to go up. If the KVP needs to go down, then the mass needs to go up. Okay. So you may be told, oh, we need to go from, like, the unknown factor is going to be one of the four. So you're going to be told 80 kVp and 50 to start, but we need to switch to 25 mass. Then we need to find the new kVp. Or you might go, oh, we have 80 kVp and we're going to go up to 92 kVp. If we started at 50 mass, what's our new mass? And the answer will be 25. So what you're doing is you're going to go, what is the missing of the four factors, right? And that is what the question will be. What is the missing of the four? You're finding for essentially X, right? And then that's going to be what you're looking for. And that's what she's going to show you on when we get back to the slideshow.
Okay, so we're back to the 15% rule. So again, as we were saying, increasing the KVP by 15% will double the IR exposure. Decreasing the KVP 15% will half the image exposure. And then to maintain the exposure to the image receptor while changing the image quality, you must change the mass as following. So again, as Professor Windmiller was explaining, if you increase KVP 15%, then you'll need to half the original mass to get the new mass. And this is to maintain this same exposure. But if you decrease the KVP by 15%, you would have to double the original mass to get the new technique.
So essentially, first you need to figure out what happened to the KVP in your question. And then you're going to decide which of those two things to do. Okay. So first you're going to decide, you're going to look at your number and change in the KVP. And you're going to go, do I need to half or do I need to double? Okay.
Okay, so this is the math problem number 2, utilizing the 15% rule. So again, to maintain the original image receptor exposure, to maintain the same exposure, what new value of mass is necessary when changing from 75 kVp and 50 mass, so that's your technique, to 86 kVp. So first we need to figure out if we're going from 75 kVp to 86 kVp, is that an increase of at least 15%? So let's do that calculation. So what's 15% of 75? So we take 75 times 0.15, which is 15%, which gives us a value of 11.25. So we'll just round it off to 11. So 11 is 15% of 75. 75 plus 11 gives us that 86. So now we do know, we've confirmed that going from 75 to 86 kVp is greater than 15%. So that will double our exposure. So then because the KVP increased 15%, the mass must be divided in half to maintain the original exposure. So again, to figure out, so our original technique was 75 kVp, 50 mass, but we want to change it to 86 kVp. So now we know we have to take this original mass and divide it in half. So the original mass, which was 50, divided in half, which is 25. So now our new technique to have that same exposure will be 86 kVp and 25 mass is the same as 75 kVp and 50 mass.
So is
And,
it always going to go up 15% and divide the mass by half? Is that like just the
yeah,
formula?
when you do your homework, yes, it'll be that way. Because we'll start simple, right? It's either going to go up 15 or down 15. So first you have to determine, did it go up 15 or down 15? And then that's going to tell you whether to half it or double it. So you're either going to divide by 2 or times by 2, depending on what it is inversely. So 75 to 86 went up 15%. So then you must go down in the mass. So you must divide by 2. So
Okay.
first you figure out what it did. And the other thing I was going to tell you guys is that when you do your homework, you can either take, you can use, it's acceptable in this math problem to round. So it just has to be close enough to 15%. Like it doesn't matter. It's like 15.2% or like 16% or something like that. Like it just has to be close. Just like where is it closest to 15? So even if you did this and you got like 11.85, it would still be 11. It's still going to be close to 15%. It's okay to round in this case.
So I just
Close
want to
enough.
make sure it's always going to be 15%, right? Either up or down.
Mhm.
Is
Yeah.
that
For
okay?
KVP.
Up or down 15, yeah.
15%.
Right. 15%. You're right. I said 15. Sorry. Yeah. So first you have to figure it out. So the next concept that's going to give us a math problem is distance. Okay. So display this distance is displayed as source to image receptor distance, SID, source to image receptor distance, D being distance. So X-ray production is similar to a point light source. Okay. So in this case, on the right-hand side, you are looking at a lamp. And the intensity of the light will be less the further away the light is from the actual like wall. Imagine we're talking about like a light source. So imagine a flashlight that is one from the wall versus one that is 20 feet from the wall. So the further away that the light source is to the object or the wall, okay, the less the intensity of the light. So it behaves according to the laws of light and intensity as a function of distance. So SID and beam intensity have an inverse relationship. It is called the inverse square law. Okay. So the further you are, the less intensity there is to the beam. That makes sense, right? Makes sense. The further away your flashlight is to a wall, the less intense the light appears at the wall, right? So the inverse square law is intensity 1 over intensity 2 is equal to distance 2 squared over distance 1 squared. So we're adding a new algebra concept in there. So same concept, we're going to be finding the missing of the 4 factors. That's how we do this math problem. We're looking for so we'll know 3 of the factors and we'll be finding the missing one, okay?
So just as the image is trying to explain, so if you're 1 feet away, the light is bright, as you can see by it, the blue, the teal, how it's a strong teal color. But if you get 2 feet away, it's only 1/4 of the intensity. So again, 2 squared is 4, so it's 1/4 of the intensity. And then if you get 3 feet, 3 squared equals 9, so it's only 1/9 of the intensity. So the beam gets lighter and lighter, or I guess less bright, sorry, less bright the further you get away. That's why it's called the inverse square law. So you're taking the distance squared inverted. That's how it gets its name.
Oh, I forgot to say, if you increase the distance from a light source, the light intensity will decrease by the square of the distance. That's the actual inverse square law. Sorry, guys.
That's what she just read right here.
Yeah. No, I didn't know that off the top of my head. No.
Okay, so this is the math problem number 3. This is the third formula that we're going to be learning. Inverse square law. The intensity of the beam is inversely proportional to the square of the distance from the source. So again, intensity 1, which is the original intensity, is divided by intensity 2 equals the new distance squared divided by the original distance squared. So this is the X-ray source. This is where the X-ray beam will be. So this is the original distance, the original intensity, which is here. And then if you double it, this is the new distance but the intensity will be by a quarter, will be decreased by a quarter.
Double the distance, a quarter of the intensity.
Algebra.
Algebra.
Okay, so here's an example. If the intensity of the beam is 40 MR, is it milliroentgen?
It is. Okay, guys, I apologize. So this is something we're going to get into chapter 9. So just believe it that milliroentgen is exposure in air. So it's just basically exposure. It's intensity of it. Yeah. MR. Just say MR. Yeah.
So if the intensity of the beam is 40 MR at the original distance of 40 centimeters, what will the new intensity be if the new distance is 20 centimeters? So again, we just need to take these numbers and plug them into our formula. So the beam is 40 MR, which is the original intensity, which would be I1. So we'll stick it here on the top. And the new distance is 20 centimeters. So 20 squared divided by the original distance, which will be 40 squared, because we want to know what the new intensity will be. So 40. So we need to solve for x. Again, algebra. So we're going to reduce this fraction because 20 divided by 40 is 1/2. So we're going to make these values smaller. So 1 squared is 1 and 2 squared is 4. So 1/4. So again, this side stays the same. So, and again, we're solving for x. So we need to
Cross multiply
to get x by itself. So we're going to do 1 times x and 40 times 4. So the new intensity will be 160 MR.
So the other thing I was going to add to you guys about algebra is that you always have to keep your numbers consistent. So it doesn't matter if you are using milliroentgens or milligrays or any of the other things. You just have to keep using the same thing on both sides. So if I told you that it was 40 centimeters and the other one was 20 millimeters, you would need to convert and use either centimeters or millimeters consistently. So it doesn't matter whether if you could do this with centimeters or millimeters, you just can't do them together. So you might, we're not going to ask you to convert, but just so you know, consistency in an algebra problem is important. So in the case of the inverse square law, it doesn't matter what intensity measure you use or what distance measurement you use, as long as you're consistent. So
yeah, just to reiterate. So again, if it's 20 centimeters, it has to be divided by 40 centimeters. So centimeter by centimeter, because you can't do 20 centimeters into 40 millimeters. You'd have to take the 40 millimeters, convert it to centimeters, and then do the calculation.
Correct. Yeah. And same thing on the milliroentgens, like I was saying. So like, let's say if I gave this to you, and it won't be like this in your homework or in the test, but if I said 40 milliroentgens and what's the new intensity in Rankins, you would have to do a conversion in there, which we will not ask you. But I just want you to know conceptually that you do have to be consistent. So your number one, you need to remind yourself on how to do algebra to find for X. Okay, that's very important. So if you don't know it now, go back and go into the resources for this week in the module, and you will see that there is a YouTube video that reminds you on how to do basic cross multiplication in algebra, and that will help you with this assignment. And the next thing you have to do is you have to go, what is this? It's a word problem. So you're going to walk in there and you're going to go, I know my formula, I memorized my formula, and then I'm going to take the information I have in my word problem and plug in the variables I know, and then find for the unknown variable. Okay, so X for your unknown variable. So when you do the homework, you cannot just see this question and write X equals 160 by MRs. No, we will give you 0. You have to show us the process of how you got there on your homework, okay? And don't feel bad if you get these wrong, okay? Again, this is one you're going to have to watch. I'll put up a wee video for you to see that. So don't worry about it.
Yeah, so it's a pretty cool YouTube video, inverse square law, that it's entertaining but also educational. Okay. This is exposure maintenance formula. We touched upon this a little bit. Also known as direct square law. It describes changes in mass necessary to compensate for SID changes while maintaining the exposure. So again, say you need to change the distance that you take the X-ray. You need to use this formula to maintain the exposure, but you'll need to calculate your new mass. So
I feel like this is the one we use the most.
yeah, definitely.
Yeah,
Well, I use the 15% rule a lot.
true. Maybe on portables, I'm thinking. Like you when you're like
Yeah.
off doing something somewhere else where you can't control the distance, like and measure it like in the
Mhm.
machine in the room, and you're like off in someone's room in a small space because there's COVID and you can't like you got to like take the image instead of like taking it where you want to inside the COVID room, you got to take it through the window from a distance, and then you got to figure out what to use because you don't want to go in the room with the patient. You want to do it from like 3 times the distance you normally would do it. This came up like all the this was like,
All through COVID.
yeah.
So I have
Yeah.
a question. Is any of these formula like problems, are they going to be on like the final?
Yes.
Okay, so can we use scratch paper during the final?
You can use a single piece of paper,
Yeah.
and you will have to show it at the beginning of the test that you have it. But but the problem is, and I'm just going to put it out there, that that the computer is going to flag you as cheating. So it's because you're going to be looking down at it. So what works better so you don't get flagged as cheating, not that we can't go look to see that you weren't cheating, but what works better is that the system in Respondus will have a calculator there for you. So,
But if some of us work
but you,
like
yeah,
writing it down, we can do that. And also,
yeah.
are we allowed to like right when the test happens or starts, write down all the formulas that we remember just to help?
Yes.
Okay.
So what'll happen is you will have to show at the beginning that you have a blank piece of paper. And then you're gonna, if what you want to do is then go down and write the formulas down from memory and then show the paper again that you just wrote them down, that is okay. And I understand that I've just given you an opening to cheat. I get that, which is why you're all adults and we expect you to be honorable, moral, ethical people. Because if you're going to cheat now on something like this, and I know you're all smart enough to do it, but if you're going to do it now, you're just not going to be able to cheat your way all the way through the program. So I'm just telling you, like, there'll be instructions on what to do about this. But the reason we'll let you do this, the reason I'm saying yes, is that the boards let you do that. So what happens is when you go in for the boards, they are going to let you, you're going to walk in with nothing. They're going to hand you something to write on that you're allowed to have. And then you'll be able to write down some formulas from memory and then use that through the course of your test. So we're going to kind of do the same thing. And there'll be instructions on how to like do that process in the final. So, and on this test. So the same thing will happen on this test when you take it. And so they'll both be like that. Yeah.
Okay, so this is the fourth formula, exposure maintenance formula. Sorry, I know we're running out of time. I'm going to go through it quickly, but we're going to review all of these formulas again at the beginning of next week. So also known as direct square law, it's to maintain the exposure. So again, the original mass value is annotated as mass 1, and the new mass value is mass 2. The original distance is D1, and the new distance is D2. So mass. So to maintain the exposure, you utilize this formula to maintain the exposure. So to calculate the new mass when you have to change your distance. So a real life scenario, again, like as we were saying, say usually we use, for radiology, we generally use 72 inches, and that's a general term for SID. Say we couldn't get that same SID, say we could only get 35 to 40, which is close enough to half. So our distance just got cut in half because whatever environmental factors. So now we'll utilize this formula to calculate our new technique. So for example, again, the word problem, if a radiograph produced at 72 inches SID distance using 20 mass must be repeated at 36 inches, what is the new mass setting necessary to maintain the same image receptor exposure, which is the same as signal value? So we had to cut the distance in half. But so what is our new technique? So again, so 20 mass was the original formula, original technique. The distance was 72 and the new distance is 36. So again, we're solving for X. So we're going to simplify this fraction, 72 divided by 36, which is 2/1. And then we'll do the square. The square of 2 is 4. 1 squared is 1. And so now we're going to isolate 1. So bring 4 over, 4x equals 20. And then now we're going to divide both sides by 4. So 4 goes into 25 times. So the new mass will be 5 mass. The new technique will be 5 mass at 36 inches. So see how it's not completely linear? It's a non-linear relationship.
I was just going to point out something that helped me when I was learning these, and that is the words inverse square law and direct square law. You'll notice that the formulas are almost identical in that in the inverse square law, it has KVP1 over KVP2, but then on the right, it has distance 1 and distance 2 flipped. So in the inverse square law, distance 1 is on the bottom and distance 2 is on the top. But in the direct square law, so exposure maintenance, when you're relating distance to mass, you have mass 1 on top and mass 2 on the bottom, and then directly across, you have distance 1 on top and distance 2 on bottom. So it's a nice way to remember it, to be like, okay, if your math problem has distance in it and then mass and KVP, if it's KVP, then you need to flip the distance so that the first distance is on the bottom. And if it's mass, the first distance is on the top. And so the name of these, inverse square law versus direct square law helps you to remember the two different formulas.
Okay, we know we threw a lot of information at you. Again, we're going to review the formulas again next week, but please, please, please try your best to do that worksheet so that way we can go through it again and see what concepts we really need to hone in on and clarify more. So,
and then, like I said, that homework assignment is due by 5 p.m. So if you turn it in if you turn it in by 5 p.m., then you're allowed to do it twice, right? So let's just say that you get it's 30 questions. If you get 15 of them right, you get 15 points. You turn it in by 5 p.m., then you get to turn it in and up your score. You have a week to then turn it in again and then potentially get 30 points. But if instead you wait until we get together next week and you go, okay, I'm going to do the review instead of turning it in, then whatever you get when you turn it in is what you get. So, if you choose to do it after and when you can see the answers and work it, that's fine. But then you need to make sure you get all of them right, because you're going to get that score. Okay. So if you want to be able to turn it in twice and get a better score, you have to turn it in by 5 p.m. Okay.
okay. Thank you, everybody. Hope we didn't overwhelm you.
Use your resources this week, guys. Use your resources.
And definitely watch those videos. They are entertaining and educational.
And remember, we know it's hard. Part of taking this class is figuring out what you need to improve on before you start the program. So.
We'll hang out here if anybody has any questions. So thank you, everyone.
Thank you.
You're welcome. I'm going to turn off the recording.